Okay, we're ready to go. All right, here we are. Welcome, everybody. Good news, everyone. It's time for another Future in Space Hangout. My name is Tony Darnell from deepastronomy.space, and today we are going to continue to our series of discussions on the 4 concept missions that are being considered as part of the next generation of space telescopes in the future. Now, in past Hangouts, we've talked about the Lynx X-ray Space Telescope, we've talked about the Origin Space Telescope, and today we're going to be talking with members of the Habitable Exoplanet Observatory, or HabEx. But before I get too far, I need to mention that these Hangouts are sponsored and endorsed by the American Astronautical Society and the American Astronomical Society, but the American Astronautical Society is gearing up right now for their annual Von Braun workshop in Alabama later this month, and I have a link to that in the description box to go check it out. And the AAS sponsor these Hangouts as a way to connect their membership with the general public with topics ranging from human spaceflight, satellite technology, and a wide range of astronautical engineering topics that are designed to inspire students to undertake space-related careers, all the while serving the professional needs and interests of its members. So I want to thank them because without their support, we could not do these Hangouts. Okay, the Habitable Exoplanet Observatory, or HabEx, is a concept for a mission to directly image planetary systems, I love that part, around sun-like stars. HabEx will be sensitive to all types of planets. However, its main goal is, for the first time, to directly image Earth-sized exoplanets and characterize their atmospheric content. Now, they'll do that by measuring the spectra of these planets, and it will search for signatures of habitability, such as water and all kinds of fun things. And it will also be sensitive to gases in the atmosphere that are indicative to biological activity, like oxygen or ozone. And today, we're going to be exploring the science of this great mission, and later, I'm going to ask about the news that came out yesterday about the possibility of this first exomoon that I know you guys are all dying to hear about. But right now, let me just say that we hope you'll leave questions and comments for our guests. We are broadcasting on YouTube, Twitter, Twitch, and Facebook. So please interact with our guests, as we pride ourselves on directly providing you with access to professional astronomers, engineers, and policymakers. So we hope you'll take advantage of that. Our guests today are Dr. Sara Seager. She is a planetary scientist with MIT. She has expertise in exoplanet atmospheres and biosignature gases. You've seen her in Hangouts before. She is also the deputy science director for the amazing TESS mission, which is currently circling over our heads, searching for super-Earth exoplanets. I have Dr. John Clarke from Boston University, who specializes in far UV observations of solar system bodies, and he has extensive experience with the instrument and mission development of the Hubble Space Telescope, MAVEN, and several sounding rockets. We also have Dr. Daniel Stern from NASA's Jet Propulsion Laboratory, who is an extragalactic observer, studying a wide range of sources outside of our galaxy, from black holes to galaxy clusters. And we have Shawn Goldman from NASA's Goddard Space Flight Center, who is an astrobiologist with expertise in various biosignatures and from their false positives with iron isotopes in the rock record of Mars and Earth, to remotely detectable gases on exoplanets. So So let me just bring everyone up here. Hi guys, it's good to have you all here.
Hello.
Hello. Hi.
Thanks for having us.
Yeah. Okay. Sara, I think it's best if I start with you. Can you give us a general summary of what HabEx is and what you hope to accomplish with it?
Sure. Well, right now, HabEx is a concept, as you mentioned, but it's just the dream of being able to go to space above the blurring effects of Earth's atmosphere and to block out a starlight so we can see planets directly. And there's actually a whole family of missions and ideas and concepts, many of them we can't even cover now. And HabEx is just like one point on that continuum of many possibilities. So HabEx is a telescope in space. It would be 4 meters in diameter. So our Hubble Space Telescope mirror is 2.4 meters. So think of it in terms of that. But HabEx has a very special ability to block out starlight in 2 different ways. One way is with the Coronagraph, and I'll let the others elaborate on this, internal Coronagraph, and the others is with the star shape, the giant specially shaped screen that would formation fly with the telescope. So actually we have these 2 different ways to find planets, and they're very complementary and can make the mission really awesome.
And so, yeah, and we're going to go into detail on those 2 aspects here in just a minute, the star shade and the Coronagraph.
I just wanted everyone to know that HabEx is sort of like a new way to piece together ideas that have been tossed around for years, if not decades. It's what we just think is the optimal way to go forward.
And this is a lot different from TESS, isn't it, Sarah? Because TESS is looking at transiting planets directly from the whole sky. Will this be a survey kind of telescope, or is it going to be a point and shoot where you have to decide where to look?
Absolutely a point and shoot. And
Okay.
so while TESS is looking at the whole sky and hundreds of thousands to millions of stars, HabEx would literally be looking at on order of 100 stars or a few hundred, just one-on-one, one by one.
And how will it know? Will it have a list of candidates already available to it, or how will it know where to look?
Well, in some ways, nature does that for us. There's a certain number of bright sun-like stars, and we would just go down the list. We might know of some in advance, but all the techniques are pushing really hard to reach down to Earth levels, and they're kind of all struggling. So we either would know or wouldn't know, but nonetheless, the list of stars is the same.
All right.
Sarah, we do have the deep dive table available to show if you wanted to go through that.
Why don't you speak to that and show it? Yeah, definitely.
Go ahead, John or Daniel. Go ahead.
So you're showing that to the.
I'm showing it now. Yes, it's up.
Okay, great. Yeah, so we our plan is to do 9 targets, really deep dive, and then we have about another 100 targets that we would do through the mission. And so these first 9 targets are already identified. They're very high value targets. They're nearby sun-like stars. And in fact, not only are they really interesting to us, but it turns out that a bunch of them have been already captured as being interesting targets from the popular culture. So I like Tau Ceti, the first one on the list, is a G8 main sequence star, and is a home port of the Kobayashi Maru in Star Trek, and it's also where Barbarella goes.
I didn't know that. I didn't know Barbarella went to Tau Ceti. Okay, that's cool.
40 Eridani is where the host star to Vulcan. And so here's the list of them. There's the Foundation series is around 61 Cygnus, which is one of our targets. Some of these already have confirmed planets, and in fact, I think since we submitted or wrote this report, 40 Eridani has a new planet around it identified.
That's right. We talked about that last week, guys, with Carol Christian, where we had the team on who took those observations. So now you didn't just pick these because they're cool and they have science fiction analog. There's actual real scientific. I mean, there's a real astronomical reasons why you guys think there's probably Earth-like or super Earth planets around them.
Well, I think Sarah explained this a little bit, so maybe let's kick this back to Sarah. I think it has more to do with the properties of the stars themselves than where we know necessarily planets are, right, Sarah?
Yeah, I mean, it's so hard to find Earths, like nearly impossible. So these 9 targets will be the best ones, the nearest and brightest sun-like stars. So that's probably why they're in science fiction as well, because they're nearby and bright and have names. So
Okay.
it's the same list.
Now, one of the things that I learned about doing over the course of these hangouts, especially when it comes to super Earths. First of all, Sarah, maybe you can tell us what a super Earth is. Let's start there, and then I'll ask my question.
Well, if super Earth is loosely defined as like a big Earth, we actually have specific numbers. We might call it like 1.6 times the size of Earth or several times the mass of Earth, but essentially it's like a big Earth. And it's easier to detect just because it's bigger and more massive.
Easier to detect by both the transit and the radial velocity method. Is that what you mean?
That's right.
Okay. Now,
and by direct imaging.
Okay. Well, one thing I've learned about super Earths that I guess whenever I read about a lot of these super Earths being discovered around other stars and other planets, for example, one of the first 2 planets that TESS has got a candidate for out of looking at Sector 2, I believe, was one of them was a planet going around its star once every 11 days. I think it was a super Earth. They were saying it was probably a super Earth, and immediately in the paper it was talk about water and atmospheres. And I'm like, how do they even begin to know that? And the guy with the Vulcan hangout taught me that super Earths, because of their size, are probably quite likely to have an atmosphere. Am I getting that right?
Well,
because of their size, they're likely to have an atmosphere around them.
Well, most planets we think are born with an atmosphere. Small planets like Earth, it's formed in quite a violent beginning with planetesimals smashing into Earth and releasing kind of whatever's inside them. And some of it eventually bubbles up to make an atmosphere. And so unless the atmosphere is lost somehow, the planet's going to have an atmosphere.
So
I think what you're talking about, though, that some planets are so big, they might have more than an atmosphere, like call it an envelope, like huge amounts of gas.
I see. So as part of the protoplanetary disk, the debris disks, and all this, just as part of solar system formation theory, you think most planets end up with a solar system or with a atmosphere as part of the process?
Right.
Wow.
I just wanted to correct a couple of things. It was from Sector 1.
Oh, sorry. I apologize. It's in Sector 3 now. You're right. Thank you for the clarification. It was Sector 1 that they had.
And it has 6 days, the planet you're talking about.
Right. Oh, it's 6 days. Okay, there were two. One was...
I think there's exoplanets. It's possible for a super Earth to be too big. If it's too big, then we have a new name, not to get too confusing on you, but we call it a sub-Neptune. And so we discriminate between like a rocky planet with an atmosphere and something like a smaller version of Neptune that has reams and reams of gas, like way too much. So there's maybe no solid surface as you know it, and it's very hot deep in the atmosphere, or envelope rather. So that's kind of maybe what you picked up on.
Okay. All right. So John, let me get you in on this discussion a little bit. You are interested primarily, as I understand it, we were talking before the hangout, you're primarily a solar system guy, right? A planetary astronomer who works on planets here in our solar system, correct?
That's correct. Right.
Give us an idea what your role is with HabEx and why you're interested in the science.
Okay. Well, HabEx is being designed to look at planets around nearby stars, which is, of course, very interesting. But when we look at a planet around the nearby star, we can only get a little bit of information about it. The resolution, the sensitivity, everything is not as good as when we look at planets in the solar system. So we would be able to use the same telescope to study in more detail the planets close by, where we can really learn about the details, the physics of their atmospheres, how they evolve over time.
Okay.
So
great.
my role on the study team is to do some studies about how we would use the telescope within the solar system and advance our understanding of planets in general.
And John,
go ahead.
Can you just say a word or two about how you think that HabEx would improve upon what we've had so far, or what we might get between now and potential HabEx launch date?
Yes, and I'm kind of looking through the graphics, but let me just start talking. The sensitivity of HabEx, first of all, would be much greater than that of Hubble. It's a factor of 2 times larger in diameter, so a factor of 4 in light gathering power. And in addition, it would be manufactured with new technology. It would have a much higher sensitivity and allow us to look at objects that are much farther away. For example, with Hubble, we can measure the ratio of deuterium to hydrogen in the atmosphere of Mars. With HabEx, we'd be able to do that on all 4 of the giant planets, on comets that are much more distant from the sun. And the ratio of deuterium to hydrogen is one of the main parameters that tells us about the evolution of an atmosphere, as Sarah was describing.
Okay, you bring up an interesting point about, I want to talk about the instrument itself now and the wavelengths that it's going to be observing in, because right now everybody, it's funny, but when I was in college and even now in the golden age of astronomy, everybody's very excited about the infrared because everybody can, a lot of things have redshifted into that wavelength, and a lot of very interesting astronomy is done in the infrared. And right now, the Hubble Space Telescope is the only instrument that's giving anything in the ultraviolet or the EUV wavelengths, and that was built into its original design. So there's nothing else really doing the ultraviolet part of the spectrum. What other wavelengths are going to be a part of HabEx?
Directing that to me?
To anyone, whoever wants to take it.
Okay, well, HabEx will go from the UV through the optical into the near infrared. And you hit on the point of UV versus infrared. In the UV, it requires more energetic processes to produce the more energetic photons. So you're looking at different physics in the 2 wavelength ranges. And in addition, in the ultraviolet, photons interact with matter very quickly. Whereas in the infrared, if you wanted to look through a dust cloud, you would look in the infrared. If you wanted to look at the upper atmosphere of a planet, you would want to look in the ultraviolet. So those are two big differences.
And the
and Sarah,
no, go ahead, Shawn.
I was going to ask Sarah, and maybe we could bring up the angular resolution chart. You know, one of the things that Sarah and Scott Gowdy, our two co-chairs, did was had us think about what kinds of other things will be happening beforehand.
Okay, which one is that? Is that the HabEx image plane one that I have?
It's
angular
resolution.png.
Oh, I don't have that one. Did you? Okay, continue talking. I'll cue it up.
Okay. And so one of the things we have to do when we look at putting anything in space is we have to think about everything that's going to happen beforehand in space, but also what's happening at the time we'd be putting it in space on the ground. Because you know, if you can do something on the ground, it's usually less expensive to do it there. And so we thought about that ahead of time. And I was going to ask Sarah, if, you know, there's this chart showing where the ELTs have the best resolution in terms of wavelength space, including these future ground-based telescopes. And it shows where HabEx kind of comes in and does best at shorter wavelengths.
I have it up now.
So Sarah, did you want to comment on that, about how we as a team took that sort of thing into consideration on the front end of the study?
The wavelength range, because I don't see the angular resolution plot. I don't have it.
Oh, well, just how we are complementary to the stuff that's already happening or will be happening on the ground.
Well, I can speak to the wavelength range, then you can fill in the angular resolution. But typically,
yep.
At least with Shawn and I and the most of the team, you know, it's called HabEx because we're a habitable exoplanet explorer. And we want to be able to study planets and look at their atmospheres and see what's in them, know if the planet has water vapor. And it turns out that molecules mostly absorb in the near infrared. That's where they rotate and vibrate mostly. So we'd really like to be able to look in the near infrared. And that's why HabEx extends to near infrared wavelengths. On the other hand, the ultraviolet is also interesting, not just for exoplanets, because on our own planet, we actually have this sharp ozone cutoff. If we could look at another planet and see that it's got a lot of radiation coming from the planet in reflected light, and all of a sudden there's nothing at a very short wavelength, that would be really eye-opening for us. And we may be able to assume ozone is on that planet, which itself is a byproduct of oxygen. Also, for the rest of the astronomy community, HabEx isn't just about planets, but it's also a general observatory. And we decided to go to the ultraviolet because after Hubble, we won't have a telescope in space for the astronomy community to work in ultraviolet wavelengths. There's actually a lot more interesting things about ultraviolet as well, about exoplanet host stars and their radiation and what it means for planet atmospheres. So at the outset, we spent a lot of time figuring out what should the telescope do. And that's how we came up with such a broad wavelength range.
And it does, this chart is going all the way from 0.1 microns to about, what is that, 10 microns?
2.5.
2.5 microns. And so and you can see the dotted line across where Hubble is sensitive to at the angular resolution of about 0.1 arc seconds, which is pretty good, all the way through a really wide length of wavelength ranges. But JWST, it's not going to go there. And HabEx is looking really good at these higher wavelengths. So this is an important wavelength range that isn't currently being met by anything except for Hubble right now, correct? So
right, and that's all great for general astronomy, but for exoplanets, you know, different telescopes really use totally different techniques. And so for HabEx, we're looking at reflected light, like the light that comes from the star and bounces off the planet. And, you know, our sun is very bright, and some like stars at yellow wavelengths, at visible wavelengths. And that's why HabEx is predominantly at visible wavelengths, where there's a lot of brightness.
Okay. We haven't talked much about the design of the telescope yet. Can somebody, I'd like to put up the exploded view of that I have here. Can someone comment on?
We're looking at reflected light, like the
someone design of the telescope yet. Can somebody, I'd like to put up the exploded view of the that I have here. Can someone comment on?
We're looking at reflected light.
Which figure is it?
Yeah, someone design of the telescope. Somebody has. I'd like to put up the exploded view of the that I have here.
You're getting a
All right. Sorry about that, guys. We had a little bit of a feedback issue, and it seems to be taken care of now. We can't have the live stream going while we're talking. So anyway, it is now off, and we're back. So back to the design, the optical design of the telescope. So we have this is something that is relatively new, I think. I only know of one other telescope that's doing this right now, and it's an off-axis telescope. And the only other telescope I know that's currently employing this is the DKIST solar telescope on Haleakala. So can someone talk to us about the optical design and maybe something like the field of view, things like that?
I could speak a little bit to the off-axis nature of it. One of the reasons that we went there is when we were looking at the exoplanet performance in particular. We looked at different designs, both on-axis and off-axis, and with different starlight suppression mechanisms. We're actually using both the Starshade and Coronagraph. We'll probably get into that later. But when we were looking at performance of the Coronagraph in particular, one thing we were finding is that if you have the central obscuration, which you have for all on-axis telescopes, the exoplanet performance, how well you do in terms of the yield of exoplanets you get, and in the amount of time it takes to get data on those exoplanets, you do much better the smaller that central obscuration is. Well, the end member for that is to not have a central obscuration at all, which you can achieve. And the central obscuration, by the way, comes from the secondary mirror. You know, you got a big primary mirror, the light's bouncing off it, hitting a secondary mirror, and then reflecting back into the optics and the instruments of the telescope. If you've got an off-axis mirror, that light on the primary is bouncing up above where the telescope's seeing. So the secondary mirror is not in the field of view, and it's not blocking you at all. And that improves everything, but it makes a dramatic difference for the exoplanet performance. And so that one change, it bought us a lot. I think it bought us something like a 20 or 30% return on how many exoplanets we'd be able to observe.
Really, just by moving this secondary mirror out of the way.
Yeah, these are really dim targets we're looking for. They are also dependent on very complex optical performance within the instrumentation, within the coronagraph in particular. And that coronagraph in particular is sensitive to that central obscuration.
Right. So if you guys follow these pink lines in this diagram, you can see where the light would follow off of the mirrors. It bounces off the primary mirror, which is off axis, is reflecting everything off to the side to the secondary mirror, and that gets you a lot more in the way of light collection, and you don't get those diffraction obstructions and things like that allow you to do more science. So I didn't realize. Would you say 30% or 20%?
I don't remember the exact number, but it was something. If I remember right, off the top of my head, it was something in that range.
Okay.
Now, one of the things that happens when we do this is, we have a team full of scientists, right? And even though we're supposed to be optimizing for exoplanet performance, we have to worry about all the other science that people might want to do with this telescope, because it's going to be the biggest UV optical near IR telescope we've ever put into space. So, Dan also is involved in this, but from a different side, right? Because if we make this change and go off axis, we have to start asking ourselves, what compromises, what sacrifices are we going to make in the other areas of science? So people like Dan were involved in making sure we didn't lose too much performance in those other areas of science that we might do at HabEx.
All right, well, let's talk about that, Dan. What are you primarily interested in? I'm getting the sense that it's not just about directly imaging exoplanets for you, as far as you're concerned. So, what are you interested in using HabEx for?
So, I would say two things. So, first off, we do call it the HabEx Observatory. And the idea is it is an observatory. It's sort of a next generation Hubble. Half the time we're planning to spend on exoplanet science, and these targets that we showed that table of before. We'll spend weeks to months going through that table. But half the time of the mission will be spent as a guest observatory, much the way Hubble is run right now, where the whole community, the whole world, can send in proposed targets, which could range from asteroids in our solar system to quasars at redshift 10 and galaxies at redshift 12. And it has a whole range of capabilities that we think will be very exciting to the whole community. I think what's really exciting about HabEx is, on the one hand, it's a 4-meter Hubble, so it's a bigger Hubble, but then a lot of these design decisions, which might not be that important driving factors for a lot of the guest observers, you make a couple of decisions like this off-axis design, and it makes a huge impact on the exoplanet science. And so we're kind of a next generation Hubble, but then all the engineering decisions were optimized for the exoplanet, really challenging case. And really very little impact on the non-exoplanet science. Our co-chair with Sara Seager, Scott Gowdy, makes this comparison that for the exoplanet stuff that we're trying to do, it's sort of like we're trying to look at a firefly next to a Klieg light, so one of these big stadium lights, and we're trying to see this little firefly a couple feet away from this big Klieg light, and they're in New York and you're in LA. You're trying to hide the light from the Klieg light so you can still see this little firefly. Except if you do the calculation, the firefly is a lot brighter relative to a Klieg light than the Earth is relative to a sun-like star.
Well, that
Dan, if you do the calculation with the firefly off, it nearly works.
Nice.
So if you got the light bouncing off the firefly, that's about the right analogy.
Okay, so that's a great segue into the next part of this, where I want to talk. You're trying to directly image something that's very, very faint next to something that's very, very bright. And so, as Sara talked about in the beginning, there's two main ways that HabEx is designed to block out the light from the star, so that you can directly image any nearby exoplanet that might be there. And as Sara also pointed out, this is reflected light, so it is. Well, I guess it's polarized, isn't it? So there's two ways that you guys are going to, not that that's relevant to anything, but I just realized that. You guys are going to be looking at blocking the starlight from something called a star shade, which we've talked about before. Now, I have this animation looping that shows a star shade unfolding and the spaceship or the spacecraft turning to face it. Does anybody want to talk about the design of this, why it's shaped the way it is, how big it's going to be, and how scary is it to see that thing unfold? I mean, wow, that looks really technologically challenging. Who can comment sort of on the star shade part of this?
I'll start, and then Shawn can.
Okay.
Well, the star shade is a giant specially shaped screen. And it is a really special shape because if you imagine for a moment putting up a big circular shape, like a ginormous circle in space to block out starlight, it won't block out the light actually entirely, because light acts like a wave and the light will diffract around the edges of the giant imaginary circular screen. And just like dropping a pebble in a pond, you'll see ripples. That distant point-like star creates ripples of light in your image with the circle. And those ripples of light can be like 100,000 times brighter than the planet you're looking for. So that's a big problem. So actually,
it could get lost in those diffraction rings then.
Yeah, and they're not perfect rings either. So it's not like it's perfectly bright, perfectly dark, perfectly bright with rings. It's kind of all a mess. Well, it's amazing, but even in the 1960s, the person who invented starshade, he's obviously not alive now, Lyman Spitzer, he actually figured out that what you need to do is called apodize. You have to go from perfectly opaque, perfectly blocked, to perfectly transparent as you go to the outer edges of this giant circle. But no one knows how to make a perfectly smooth, perfectly going from completely blocked to completely transparent. And it actually worked out mathematically that the equivalent could be a shape like what you're showing for the star shade. You could have this shape of like a ginormous flower with petals. The petals are a very specific shape. The number and the size of the petals has to be made just so. Although there's a whole family of solutions, you pick one that works for you engineering-wise. And so Lyman Spitzer figured that out. And the star shade has to be on the order of tens of meters in diameter. And it will formation fly like tens of thousands of kilometers from the telescope.
So this is a little not to scale, this particular animation, because it looks really close, but it's going to be tens of thousands of kilometers away from this shade then. Okay.
Yes.
All right. So and how big did you say the star shade itself was?
This one I want to say is on the order of 60 meters.
60 meters. Okay.
It's kind of been going back and forth. We had a 72 diameter version before, but I think it's come down to about 60 meters now. The smaller the better, because the star shade lines up perfectly with the telescope, blocking out the starlight. But when it wants to move on to the next target star, that star shade and its spacecraft have to move across the sky to the next object. And it's kind of fuel limited because you only have so many times that it can keep moving.
That's a good point. So, what is the how much fuel are we going to put on this mission? What's the mission length going to be designed for nominally?
I don't have a number for fuel. I don't know if you do, Shawn. We usually just try to think of it in terms of numbers of retargets.
Yeah, I think, and it's probably around 20 a year. Is that right?
Yeah, I think around 20 to 30.
And the mission length overall is designed to be how long?
It's designed to be 5 years.
Okay.
5 years, let's say, but it should launch with 10 years of consumables. I mean, everyone likes to hold margin. If they say, hey, Tony, your job is to make this thing last for 5 years, your little part of the telescope. Like, you don't want to be the one to make it fail.
Yep.
So I'm going to make mine a little better. I'm going to make it to last maybe 7 years or 8 years. So we hope it's 10, but it's specified for 5.
And nowhere is that thinking better illustrated than with the Kepler Space Telescope, which was only designed for 5 years and is just now starting to run out of fuel. So it is.
Or, for example, the Mars Curiosity rovers.
Yep.
Not Curiosity, the twin Mars rovers.
Mars exploration rovers. Yeah.
Yeah, Mars exploration rovers. They were only supposed to last 1 Martian year, and they kept going for a decade or more.
So that kind of thinking is really good. And that's even true with tests, right? I mean, you guys are nominally going to work for 2 years, but you're I think, fully expecting, or hopefully, I think you've got enough to keep going for longer than that, right?
Well, yeah, the mission is funded for 2 years, but it really could last for a decade, even longer, actually, because the orbit is very stable, and TESS doesn't really have to expend fuel. It doesn't really have any moving parts on it. And there's not a lot that can, knock on wood, go wrong. Last quite a long time.
Okay, well, while I'm showing this animation still, where in space is HabEx going to go? Is it going to go to the L2 point? Is it going to go somewhere else? Where will HabEx go?
It will probably go to L2. Okay. The thing for Starshade is you have to realize that it has to formation fly very tightly. And Earth's gravity gradient is horrible for formation flying. You want to get far away from any gravity you can.
Good point.
Let's just call it a popular place because Earth is so bright and hot, it's bad for astronomy. It creates a lot of contaminating light as well.
Okay, well, I've got a couple of questions coming in about the Starshade, so let me get those in. James Dugan wants to know, what's the service life of the Starshade? What's the service life of the Starshade? It would have to have a lot of fuel to last, and we've already talked about the fuel part. But what about everything else? What do you think once it's unfolded? That's really there's no moving parts, right?
Yeah, there's no moving parts of Starshade. I mean, it's got to be really flat, and there are specifications for how flat the petals have to be, and how they can really just be, in plane, like lined up together.
Well,
the surface, I don't know what he means by the surface. Go ahead.
If we had an infinite amount of fuel, my understanding is the next thing that would limit it would be micrometeorite impacts, but it's even being designed with 2 or 3 layers so that as long as the impact comes in on an angle and not perpendicular to the Starshade, the light would not get through all 3 holes that the micrometeorite would make. Okay,
well, Adam Synergy, I think, is asking a question I think all of us are sort of wondering too. I know I am. Unfolding and flying a Starshade in formation with the scope sounds difficult. Are the team confident it'll work? Looks a lot like JWST when I watch that animation. How confident are you?
You have to understand that there's still a ways to go in development. And the Starshade is being, at smaller scales, tested and deployed on the ground. It's an ongoing process, actually. But you should also know Starshade has heritage. It doesn't just invented out of the blue. It turns out mostly what happens in space engineering is building upon something that's been done already. And if you see in the early part of the animation, how the Starshade is stowed and deployed, minus the petals, unfortunately, that's been used over and over again in large radio deployables in space. So the Starshade, deployment itself, the core part of that, this inner so-called truss, we're very confident that will work. And with the petals, the team is constantly making changes and doing tests to make sure that when the time comes, it will work.
Was anything gained from experience on the James Webb Space Telescope, or was this a pretty different and parallel effort?
Yeah, it's a different and parallel effort right now. I mean, there is a different Starshade design that you didn't show that is similar to James Webb, actually. And that other design comes from Northrop Grumman Corporation, the same place that was the main contractor for it and also built the sun shield that, it has the James Webb sun shield has these telescoping poles, and the current version of Starshade doesn't. So just call it different, but it has some things in common.
Okay.
But
and there's lessons learned, with all this stuff. we're always trying to incorporate the stuff we learned from the stuff we do before. So, we're in the same meetings and conferences and sometimes on the same teams as the people that have been working on Webb, and they're telling us, like, don't go that route for the Starshade deployment, because we know that can be really difficult from some of the experiences we've had already. But that's more of like a lessons learned than a specific heritage transfer, like Sarah was talking about.
Okay. All right. I need to take a quick break here and remind everybody you're watching a Future in Space Hangout from Deep Astronomy that is sponsored by the American Astronautical Society. Those guys are making this happen, so I want to thank them for taking the time out, or for supporting these hangouts and bringing all this really great information to you. Okay, so we've talked about the Starshade. There's another way that you're going to block out light from the host star, and that is with a coronagraph. Now, I have another animation playing that shows, it's a rather long animation that shows the path of light going into the telescope. But who wants to talk about the coronagraph part? And how will it work in conjunction with the Starshade? Anyone?
John, do you want to try that, or someone else?
John?
Sean.
Is he there?
Okay. So was it John or Sean? You said.
Sean. I thought.
Sean. Sorry. Go ahead.
Yeah. Okay. I can try to take that one.
Okay.
So I heard this wonderful analogy of someone being strong enough to move a piano but nimble enough to play it. And that's the goal for HabEx, is we want it to be powerful enough to get really good information on individual exoplanets, but also nimble enough to find a bunch of exoplanets. Because, and Sarah was talking about this at the outset, our hope is that improvements in ground-based and space-based observations over the next 10 years give us this wonderful list of known, potentially habitable exoplanets that we would point HabEx at. But as of today, we don't have that list. We've got a star list, but we don't have the exoplanet list, especially for the potentially habitable worlds. And so the job of the coronagraph will be twofold. First is, if we don't have that list, to find it, because the Starshade, you got to move it across the sky to your new target before you can point the telescope there, and that takes time. With the coronagraph, you just point the telescope wherever you want to go, and you can make your observation on that new target, and that's much faster. So it's going to that speed is going to let it find targets more efficiently, more quickly over time, or especially early on in the mission, that the Starshade would follow up on. And that pairing makes HabEx much, much more powerful. The second thing it'll do is, even if we know where our targets are, there's all this other information we're going to want about the planet. The Starshade and the coronagraph, we think a lot about getting the spectrum, sort of the color information from these worlds. That's how we're going to look for these potentially biogenically produced gases. It's going to be how we characterize the climates of these planets and look for water vapor in their atmospheres. But we also want to know things like, how big are the planets? What are their orbits like? How much energy do they get from their host star? And what are their brother and sister planets in the same system doing? For those kinds of things, having multiple observations of the same system is going to be really helpful. And that nimbleness of the coronagraph is also going to really help. In terms of how it works, it also cancels out the light at the center of the image, but it basically does so inside the telescope. So the advantage of the Starshade is it's blocking the light before it ever hits the telescope, which makes handling the optical aberrations of the telescope actually simple. You don't have to worry about it at all, because you're canceling the starlight before the telescope messes with your wavefront. With the coronagraph, the challenge is, once the light hits the telescope, it's not perfect anymore, which means canceling out the light at the center of an imperfect image, that's even harder than canceling out the light of a perfect image. And so there's all these extra burdens, both on the telescope itself and on the optics internal to the coronagraph instrument that puts on us. So it does have a separate set of challenges associated with stability of the telescope. We chose a coronagraph that the telescope should be relatively insensitive to instability, so the telescope doesn't have to be quite as sensitive as some other coronagraph designs. But that's one burden that we have on the mission. And then the other is, we actually have to develop the technology to cancel out the starlight inside the telescope and cancel out any wavefront errors the telescope induces.
Now, that deformable mirror that's showing in the animation, that's part of that, right? The canceling out of the starlight.
Yeah, so basically the whole time you're doing an observation with the coronagraph, you're doing simultaneous observations to see how bad that wavefront is from the telescope. And then you've got essentially a deformable mirror that can adjust in real time to cancel out those effects. You almost are putting in the opposite error to what you're seeing to cancel it out. And that has to be done over time, because sometimes very, very, very small, like nanometer size changes to the telescope can affect what you're seeing downstream in the coronagraph. And those small changes can be happening during your observation. So you don't just kind of have one mirror, deformable mirror position you lock into place. It kind of has to be always varying.
Okay. And and this is this a different light path than what would be used for the star shade?
Yeah. So one of the things that this means is you've got all these extra optics to correct things with. And extra optics in general are bad because every time you're reflecting light, you're losing just a tiny bit of it. And if you lose a tiny bit of light and a tiny bit of light and a tiny bit of light and a tiny bit of light, eventually you're talking about some real photons here. So, this is one of the other advantages to the star shade is because you don't have to do all those corrections, you don't have all those optics, you don't have all that the loss of photons, and the star shade becomes much more efficient. We have a separate instrument for the star shade to take advantage of the fact that it doesn't need all those extra reflections and optics in the light's path. So we actually have one instrument for the coronagraph stuff. We have a separate instrument just to do the star shade observations with, so we can take full advantages of those star shade advantage.
Yeah, but one of the really cool parts of the coronagraph is getting that spectra. Can you get that from the star shade side of things, or is it only from the coronagraph?
Yeah, and we can, and it's even you can even do a broader wavelength range with the star shade than you can with the coronagraph. So the coronagraph, because you're doing that cancellation, you can only do it for a narrow band of light at a time, like 10%. So if you're looking at the 1 micron wavelength, you can only do from like 0.95 to 1.05 microns. The star shade, because you don't have to worry about that cancellation, you don't have that narrow, what we call a narrow bandpass, you can actually look at a much broader bandpass of light, like 30, 40, 50%. So we might be able to look from 0.5 to 1 micron instead of having to look from 0.95 to 1.05 microns. Which makes, again, our observations more efficient with the star shade. So and this is, again, why but we want both, because the coronagraph is going to be really good for finding the targets and determining their orbits and their masses. The star shade's really is going to be what we use to do the characterization, the really detailed work on these worlds to find out what they're like.
Okay.
Sarah, did you want to add to that story?
He covered it. It was kind of complicated to explain, but Shawn covered it mostly. One's good for finding, one's good for spectra.
Yeah, and I want to show, before we move on to a couple of questions here, I want to show this image plane diagram that is highlighting all of the different instruments and where they're going to be shining onto the image plane of the telescope. Can someone maybe describe this for us? We have things that says FGS1, FGS2, FGS3, and then HWC.
Want me to do it?
Yeah. Tell us what we're looking at here. What this is?
Yeah. So there's 4 main cameras on a HabEx, and then there's 4 fine guidance sensors. So those are for pointing and keeping stability of the telescope. The other 4 aspects are the camera. So in the center, we have the UV spectrograph, this UV camera for doing a bunch of astrophysics from exoplanets to, studying Jupiter and Saturn. We have the coronagraph and the star shade are those dots to the left and to the right. And then the HWC is the HabEx workhorse camera, which is a very broad use, UV to infrared, imager, and spectrograph, useful for all sorts of science as well.
Does that say 3 minutes by 3 minutes?
3 arc minutes by 3 arc minutes.
3 arc minutes by 3, right. Yeah. Wow, that's pretty wide field then.
A little bit bigger than Hubble, but yeah.
That's pretty good. That's bigger than I thought. Okay. Wow. So so we've got a lot of instruments and we've talked a lot about the HabEx deployment. Where are we now in the planning of this? You guys, because you're part of the decadal survey, or you're trying to be considered among other instruments, can you give us a sense of what are you guys doing now and what's next for the mission?
Well, we're trying to wrap up our project now. We had studied it for a couple of years. We have an interim report and we're working on a final report. What is our final story? And this would be, let's say, a couple hundred pages. And that is input it has an executive summary though, which is more readable. And that will go as input to the decadal survey so that the people who are chosen to help gather information and consensus on what the next big mission should be will have every detail they need.
And this is due when, Sarah? It's like early next year, isn't it?
early next year, let's say. I think we're trying to finish by the end of this calendar year, but it takes a lot of revisions and internal revisions to get it right. So,
and then, do you have any idea when a decision might be made on this, or is it?
Well, let's say the decadal takes a couple of years, and the mission's by no means ready to go. I mean, we talked about Starshade before, and how do we know it will work? We're confident, extremely confident, we can build something that works, but we still have a ways to go. So it could take years. I want to say, just to throw out a number, several years, 5 to 10 years to actually build the thing and get it ready to launch. So it's still quite a ways off, no matter how you look at it.
Do you guys have to worry about cost at this stage, or is that not part of it yet? It's all about feasibility and science.
It's definitely part of it, and we don't have a number we can share with you right now.
Sure.
But we will have internal costing processes, and we get an external cost by like an independent body will assess our cost and risk, and all of that information will go to the decadal so they can consider it.
Great.
Okay. Sarah, do you want to say a word just about our approach to cost and risk? Because I think that's one of the things that we've tried to be mindful of, right? Is
Shawn?
Well, one thing we want to make sure of, and Sarah referred to a range of missions or a range of options to head into the decadal survey for this sort of direct imaging of exoplanets. We've studied stuff in the past. Actually, Sarah led the XOS study, and there was also a corresponding XOC study, which is sort of a probe level sub $1 billion Starshade or Coronagraph mission. And the LUVOIR team is also looking at less cost-constrained versions of a direct imaging exoplanet mission. And for HabEx, we've been thinking, what does a flagship look like that can do this science, but be very constrained in terms of not at the probe level, but also not totally unconstrained in terms of technical risk and cost. So we've been mindful of, when we think about the Starshade, when we think about the Coronagraph or the telescope or its instruments, we want to make sure that we are limiting ourselves or utilizing things that are well developed technologically, that we wouldn't spin up a whole team of engineers and scientists to wait around while we're developing the technologies for this, that everything's kind of ready to go when we get the green light to proceed with the project. Is that about right, Sarah? Is that fair?
Yeah.
Okay. So I want to we only got a few minutes left, and I've got a bunch of questions I want to ask. I want to start with getting you guys feedback on the big news yesterday. A lot of people have been asking in the chat, so I'm just going to sort of combine everybody's question into one. And yesterday, it was announced by some astronomers that the Hubble Space Telescope has a light curve that might suggest that the first exomoon has been actually seen in the transit of a star. Can you guys comment? I mean, Sarah, you were quoted, I think, yesterday from National Geographic, where I think you said you would like to see more confirmation, some more observations.
Is that I just can repeat what the author said. I actually have the paper right here because I've been reading it.
There we go.
You don't really even need Shawn or I or anyone on the call, or John or Dan, to say anything. They call their title Evidence for a Large Exomoon Orbiting Kepler 1625b. And their conclusions actually say that, all in all, it is difficult to assign a precise probability to the reality of the moon. Formally, the preference for the moon model over the planet-only model is very high. On the other hand, it's a complicated, involved analysis, et cetera, et cetera. So I don't think we really need to say much. It's exciting if this could be a moon, but you might call it like a exomoon candidate. And it's just so hard to get data and to analyze stuff. So I think you see this more as a progress report than a discovery, and that's how the authors describe it. So they want more time. So I wasn't like giving really even my own opinion. It's just need more data. It would be very unusual moon, Neptune size and Neptune mass. Like it's more like a double planet if it's really.
That's right. We're talking about a giant planet already, and with a moon that's basically the size of Neptune, if it is there. So you're right. That is a very strange. How uncommon do you think that is, Sarah?
I mean, we don't know because there aren't any. So
Yeah.
Fair enough. That's true. Okay. What about exomoons in general? I mean, do you think everybody in my audience, for some reason, every time we talk about exoplanets, everybody's jazzed about exomoons.
Everyone wants to find Endor.
I guess so. Is that what it is?
Yeah.
What are you guys' opinion? I mean, to me, I would like to see an exoplanet of any kind, super Earth, whatever it is, with biosignatures on it of some kind. But what are your hunches? Are exomoons a better place to look? I mean, in our own solar system, they seem to be. And maybe, John, you can comment on this, where we've got Enceladus, we've got Europa, and even Titan. People are thinking about. So I don't know. Are exomoons a better place to look for life? What are you guys' thoughts on that?
I just want to say that as we love finding stuff, and I guess your audience shares that excitement. So we just want to find, like, it doesn't really matter in a sense if it's good or bad, but in astronomy, though, we're so biased really to what we can observe. And like, as you know, we can find planets, but it's hard to study their atmospheres. We talked about HabEx and how complicated it is. And moons are just harder and more complicated. So we don't really think about the search for life on exomoons because we can barely study the planet, let alone the moon.
Could it be? I mean, if you think about what we're planning to do is we're going through all of this amazing technology development and work just to block out the starlight so we can get that 1 pixel of light from the planet. If that 1 pixel of light has a gas giant planet and an Earth-sized moon around it in the habitable zone, now we have to worry about canceling out the light from the gas giant to get at the, whether or not there's oxygen on that moon. It's theoretically possible, but that's a whole nother thing that we have to figure out how to do.
And can this be something that, I guess I'm trying to think, what kind of observations would you need? Can you do this from the ground? Can ground-based telescopes help, or do they have to be space telescope observations?
To find them, or
to be able to I guess and I mean, what Sarah said is a point well taken. Seeing these dips in brightness are very hard to make, period. But can we do it from the ground, or do we need something like HabEx, or even something bigger to see these things with? Exomoons.
Well, with HabEx, we wouldn't be able to separate. Like, okay, we were talking about the Firefly and the Searchlight, or the the Sage Light, and you can barely separate the planet and the star. So you cannot separate the moon and planet. Not going to happen for that. I mean, if it's a transiting Neptune-sized moon, you may have a chance of studying it with the James Webb as it goes in front of the star, and the starlight shines through the atmosphere. So that's possible.
Yeah, and it's important to realize that a lot of this separating ability comes down to resolution, which comes down to the diameter sizes of primaries and a variety of these. And even though this will be a 4-meter telescope, even things like JWST with its segmented mirror would have a hard time being able to separate these things if it even had a way to block out light. Wait a minute, it kind of has. It has micro shutters. I don't know if those can act as a coronagraph or not. Maybe they can. I should ask those guys. Okay, so
Webb does have a coronagraph on board, but it's not going to be at the level we need for this kind of observation.
That's what I thought. I thought I heard something about that. Okay. Well, let me ask a couple more questions here. Superluminal wants to know, why does HabEx use a separate star shade and JWST use an attached star shade? It's not really a star shade. It's not really a star shade.
An internal coronagraph?
I think he means sunshade. Maybe they're getting confused.
Yeah, I think superluminal. Yeah, I think you're getting a little confused between the star shade that will block out the star's light with JWST's sun shield, which will cool the telescope. I think that maybe
it blocks out our sun.
Yeah,
just to cool.
Right, our own sun. Right. So, John, I want to get back real quick. Go ahead.
Oh, go ahead. I was going to say, just to be clear, the reason that HabEx doesn't have a sun shield as well is because it's got that baffle, and that's what's doing the job on HabEx that the sun shield on JWST is doing.
Okay.
That tube is blocking out the light from the sun.
So, John, while I have you here, I would like to ask you that question about have you comment on the moons of our solar system and what do you extrapolate to others? I mean, Sarah's right. We won't be able to see them directly anytime soon, but what are your thoughts on exomoons versus exoplanets for any kind of habitability function? Does that make sense?
Well, first, I'd like to thank other people for talking, giving me a few minutes to think about that one. I think the main comment I can make is that the solar system may not be a very good example of what's happening around other stars. I mean, nobody expected, based on the solar system, to find Jupiter-sized planets in the orbit of Mercury, so we have to be careful about that. But you said that you thought moons would be more promising in our solar system to find life. And I think we can say a couple of things. One is that if you're looking for frozen water on the surface, that's where the moons in our solar system look promising. But if you're looking for an object that can hold on to an atmosphere, that's more likely to be a planet. You need something with enough gravity to hold on to the atmosphere. You're looking for a planet at the right distance from the star to have the temperature able to hold on to water. I think there's a wide range of parameters that you have to look for. And I'm not going to speculate. I think we need a mission to find these objects and learn what the properties are before we can really answer that question.
That's a good point. We tend to let things run away from us, don't we, when we think about these things? Dark Time is asking on Discord, what are the trade-offs of using an off-axis mirror? Because this isn't a new idea. What are the trade-offs between using an off-axis mirror and a standard one?
Well, it's really hard for the chronograph to work with an on-axis mirror because not only, as Shawn was describing, the secondary blocks out some light, but it creates a diffraction pattern. And that's hard for the chronograph to work with. But the off-axis makes the telescope bigger, essentially, because you have this big piece sticking out the side.
Okay.
So it's really a mass or size versus obscuration.
Okay. Condor Boss is asking, and I think you answered this a little bit, Sarah, already. By direct imaging, or by direct, let me start again. By directly image, I assume the planets won't be more than a pixel? What will the planet look like?
It's not going to be a beautiful Apollo image of Earth, for example. It really is a point source of light, just a dot. But yeah, it's because of the telescope optics, it's a pixel or a few pixels, but it's really just a pixel.
Okay, so D-Physics Star, we've already answered this one. Talk about exomoons. HabEx will be able to detect exomoons in general. Sarah's just answered that, so not really. What about Earth-sized planets? Planets in the habitable zone in circumbinary orbit around a binary star. Would HabEx be capable to detect that kind of a planet? These would be planets in orbiting around a binary star system.
Well, right now, it's so hard to block out the light of one star.
Right, I was going to say, wow.
We don't know how to do two.
But
we talk about it. You can have the chronograph and the star shade, so why not use both of those and try to do it? So that's kind of TBD.
Yeah.
Great question, though.
Yeah. No, pleasing some people. It's not enough to block out one light, is it? No, one star. No, you want to do several.
Well, no, it's a question because many of the nearby stars are in binaries.
Mm-hmm. Right.
So we'd really like to figure out how to do this so we can buy back some stars.
Mad End wants to know, can Starshade and HabEx launch together when it comes to overall mass? Anybody? How will they launch?
That's the goal.
You want to launch them together, same rocket?
Well, and we're designing to do that. A lot of it's going to depend on what rockets are around, when HabEx launches in 10 plus years.
And we're looking at both single rocket and two rockets.
Yep.
Larry Keese wants to know, because the stars are everywhere, how much movement of the big shade would be needed to have a 2-star blocking methods? Oh, wait, I'm sorry. Because the stars are everywhere, how much movement of the big shade will be needed?
Well, stars are everywhere, but as you heard from Shawn earlier, or Dan, there's 9 amazing target stars and about 100 extra stars. Those are spread all around the sky, and they're not all in one place because we're just going after the brightest sun-like stars. So
or the nearest.
Yeah. Okay. And from, let's see, Christian Zhao, I believe, from Facebook is asking, what kind of orbit will Starshade and HabEx look like? You said it sounds like you don't have that nailed down yet, do you? What kind of orbit?
They'd both be at L2.
You're pretty much thinking L2 then?
Yeah.
Yeah. Okay. And let's see. A D-Physics Star again. I wonder how Starshade or Coronagraphic will be able to block the light of 2 or 3 stars. We've already, okay, you guys are going on about 2 or 3 stars here. Let's see. Okay, but wouldn't it be possible, this is D-Physics Star again, to get the exoplanet plus the exomoon spectrum and separate it like they do in the spectroscopic binary stars? I mean, you guys showed that in the animation, right? Where you did have a spectra of both a main planet and a moon. At least that's what it looked like in the animation. Is that something you can do?
That was 2 planets. Sarah
2
Sarah
planets.
referred to this earlier.
Go ahead.
I mean, maybe.
Okay.
I think that's the one thing you could try. Sarah, I don't know. Do you've got more expertise here than me? Do you think that would work?
I'm not sure what that.
Like if we had if there was an exomoon around an exoplanet, could we do a block out the starlight and then do a transit spectroscopy observation of the exomoon crossing in front of the exoplanet?
Sounds like an interesting idea. I'm not sure if it's feasible, but that's a good one.
Okay. All right. Well, that is it. We are out of time, folks. I'm going to stop here. We are need to be respectful of my guests this time. This has been a Future in Space Hangout. I want to thank my guests, Dr. Sara Seager from MIT. She's a planetary scientist there and one of the co-chairs of the HabEx team. Daniel Stern from JPL. Shawn Goldman from Goddard Space Flight Center, an astrobiologist there, as well as John Clarke and Daniel Stern. Daniel's from JPL and John Clarke from Boston University. I want to thank you all so much for taking time out of your day to let us know about this mission. I can't wait to find out, and it sucks that I got to wait years before I find out who's going to finally get this. But HabEx is the one that I'm personally I want this one because this one is amazing. I hope we get this. I wish it didn't have to be just one choice, but I hope you guys will consider coming back again when we know more about the status of the mission and whether we're going forward or not, to let us know maybe some more details about the technology and the science mission. I have one final question. Will this have a time allocation committee team on it to decide how the telescope gets used? If it does get selected? So it will. Yeah. Okay, that's what I thought. Okay. All right, folks. Well, thank you all so much for watching. On behalf of all my guests and Harley Thronson, who will be back next week, and Carol Christian, who will also be back, we're going to be with Astro Coffee Hangout. Thank you all so much for watching. And as always, keep looking up.
Thank you.